Good morning, all. We're going to perform an experiment with a capacitor and a relay coil in series connected to this 24 volt DC power supply. The light bulb here is across the contacts connecting this light bulb to 120 volts AC single phase, so that when we apply 24 volts to our series capacitor and coil, the relay will energize as the capacitor is charging. And at about 19 volts, give or take a few, this relay will de-energize. Now the light bulb will indicate to us that the relay is energized or de-energized. The light bulb being because it's kind of hard to see these small contacts from way up in the air where y'all are at. So we'll be able to tell that the relay is on or off by this light bulb being turned on or off. Now I've got three different values of capacitance. We'll start out with this smaller value here of 4700 microfarad at 50 volts. Then we'll go to 10,000 microfarad at 35 volts, and then we will go to 15,000 microfarad at 50 volts. And we'll watch the differences between the three capacitance and how long this relay is energized while this capacitor is charging. Now, I've got a drawing over here of the circuit, and we'll get up close to this drawing here real quick, and afterwards we'll hook up the circuit in accordance with our drawing. Let me get the camera closer to that drawing and we'll see the circuit. Here's the circuit that we're going to experiment with. Now starting out up here is our 120 volts AC from the wall, from the power plant, coming through the light bulb on the hot side, through the relay switch. When it is energized, this light bulb will be turned on, and on the other side of the switch we have neutral. And it doesn't matter whether you have neutral up here or hot down here or L1 or L2, whatever you want to call it. It doesn't matter. AC is going to flow through this circuit right here, regardless of whether you have hot or neutral connected to it when this switch is closed. So polarity here doesn't matter. Down here is our relay coil, and I measured our relay coil at 615 ohms. This is a spike suppression diode that when we turn the relay off and the high voltage generated across that coil from the magnetic field collapsing across the windings of that coil, it will keep that high voltage in this circuit right here until the magnetic field is fully collapsed. Here's our capacitor that we're going to charge up when we apply 24 volts DC to this circuit right here. As it is charging, current is flowing through this circuit, energizing the K1 relay. When we change these values, when we increase the capacitance, the time it takes to charge this capacitor increases. So we're going to start out at 4700 microfarad and see how long it takes for this capacitor to charge. Then we're going to go to 10,000 microfarad and then 15,000 microfarad. Now let's hook up the circuit. We'll take the 4700 microfarad capacitor first. Alright, here is our plus 24 connection. It goes to the positive side of the capacitor. This side here indicates that this is the negative side, and with no marking, that's the positive side. Now we'll take our black lead and we'll go to the relay coil on the anode side of the spike suppression diode. On the anode side, don't get it backwards. If we forward bias our connection to that diode, we won't energize the coil. All the current will be flowing through the diode and bypass the coil. So we don't want to do that. So here is our negative side of the capacitor connected to the coil with the green wire on the cathode side of our spike suppression diode. Now we're all hooked up. I've got the light bulb kind of off the screen so that when the relay is energized while that capacitor is charging and the light bulb turns on, I don't want to blind the camera. Okay, all right. Let's see what happens. There. The capacitor is charged probably up to about 19 volts, and at that voltage the relay turned off and the light bulb turned off, indicating that the relay is de-energized. Now the capacitor is still charging. It will charge to full charge, oh, I don't know, this one right here, maybe a minute and a half thereabouts. So, in fact, let me put a voltmeter on there and you'll watch it continue to charge as this relay right here has turned off. Get my voltmeter put in there. You can see where the relay turns off, at what voltage the relay turns off. The circuit is still turned on, so be careful. Don't short nothing out. Clip across that capacitor right there. Yeah, we're probably at full charge now. We have 23.90 volts across that capacitor. Let me turn the power supply off and we'll watch that capacitor discharge. There we go. We'll still be able to see the light come on, but we'll also be able to read what our meter says. Now, we got 43 millivolts still discharging, but let's go ahead and apply 24 volts to that circuit. There, about 19 volts of charge across that capacitor. The relay de-energizes. And look, we're continuing to charge up. I think we're at full charge at 23.9 volts. We're almost there. There. That's about as full charge as we're going to get. Okay, now we've seen the voltage across the capacitor gradually increase. Let's see what happens to the coil as we apply 24 volts DC to this circuit. Now we know that when this capacitor was charging, the relay was turned on. So that would indicate to us that we'd start out here at a higher voltage, and as the capacitor is charging, this voltage right here will be decreasing to a point where the relay will turn off. So let's see if our theory is correct. I'm going to clip onto the spike suppression diode. Move my meter leads here a little bit so y'all can still see that meter. Okay, now right now on the coil we have a negative 5 millivolts. And here we go. We're going to turn the 24 volt DC power supply on, and let's try to catch at what point this relay turns off. About 4 volts this relay turns on. I think I saw 4.3. It happened pretty quick, didn't it? But as this capacitor is charging up to the voltage across the coil is going down. That's why when we start out with current flow in the circuit, while that capacitor is charging, this relay is turned on. We have current flow through the circuit, and we have a high enough voltage across the coil to turn it on. And as this capacitor charges up, the voltage here goes down, the current goes down, the voltage goes down here, and the relay turns off. Let's look across that coil again. What we're going to do now is going to turn the supply off. The power supply is off, so this isn't going to increase, but the capacitor is discharging. We saw that a little bit ago. The voltmeter on the power supply says we're at 0 volts. Let's turn the circuit on again. We're looking at the coil of that relay. About 4.4 volts it turned off. We had 4.4 volts across the coil. Let me disconnect our voltmeter from the coil of that relay. Now we're going to install the 10,000 microfarad capacitor. Let's take that one out. Don't hook these up backwards. Get the polarity right. We don't want to reverse the polarity on that capacitor. Let's put our voltmeter back into the circuit. We're going to connect across that relay. Applying 24 volts to the circuit. Almost at 19. Looked like about 18.8 volts it turned off. But did you see that it took longer? That took quite a bit longer. We're still charging. At 23.9, our capacitor will be fully charged. And look, as we get to that 23.9, the charge rate starts to slow down. I just thought of another experiment we could do while we're testing timing of charge and discharge of capacitors. What if we take in series two capacitors? These are two 10,000 microfarad capacitors. What if we series them, and what if we parallel them? Let's try seriesing these two capacitors first, and we'll see how long it takes to charge. Turn our meter back on. Put this ground lead of our meter on that capacitor, on the ground side, the negative side, and then we'll put the positive lead on the positive side of that capacitor there. Then we shall series them with this clip lead. That was pretty fast, wasn't it? That was near as fast in time as our 4700 microfarad capacitor. Okay, let's unhook this from here. Let's bring this over here. Now we're going to connect both negative sides. Put our voltmeter back in there, connect our power supply. Now we're going to parallel both positive sides. Okay. So now the two capacitors are in parallel. Let's see how long it takes. Notice it takes longer when we parallel those two capacitors to reach 19 volts. There's 30 seconds and we're still charging. There's a minute. We're still charging. Minute 30 seconds. We're still charging. Well, it's much greater than the minute I thought it was going to take. 2 minutes. I think that's as far as we're going to go. We're going to call it 2 minutes. Still charging. 23.81. Do you see the difference in time between series and parallel capacitors? Time to charge. Look, we're still charging. Ever so slowly. All right, folks. I took up a lot of your time, but I hope it was interesting. Looks like we're going to stop right here at 23.8. All right, all. Stay dry out there. It's raining and cold here. Okay, let's turn that power supply off. We got to head to the hooch. Got some birds to feed. We'll see you next time.